So we had started rate of reaction. I told you that everything depends on collisions, like particles bumping into each other. And when you talk about collisions, you talk about them in two ways. One is like how frequently are they colliding, and the other one is how effectively they're colliding. Like the particles might be colliding a lot, so they would have a very high frequency of collisions, but there would be zero reaction. That means the collisions are of no use. Maybe they're not energetic enough, they're not violent enough to lead to a reaction. So they're not effective. Uh, so they're not effective. One second. So basically, you had two things going on: frequency and effectiveness. And maybe the collisions are not very frequent, but they are very effective. Like you have 10 collisions, and out of the 10, 8 of them, there's a reaction that's happening. So that means the success rate of the collisions is a lot. So both of these factors are kind of independent. So the first one was temperature. Like if you increase temperature, the kinetic energy increases. So the particles travel faster. And when they travel faster, they hit each other more frequently. Plus, they're also hitting each other with a lot more force because they're more energetic. So they're also more effective. So when you increase pressure, for pressure, the thing is that it only applies for gases because gases are the only thing. They're the only thing that is compressible. So the particles become closer together. There's less spacing. They become closer to each other, and when they're closer to each other, they bump into each other more. So the frequency increases. They just bump into each other a lot more. The effectiveness remains kind of the same. Uh, they're not hitting each other with greater force. They're hitting each other in the same way, except that they're hitting each other more frequently. Same goes for surface area. You've got more frequent collisions, concentration as well. When something is more concentrated, the spacing is lesser, and they bump into each other a lot more. So frequency increases. So you get more frequent collisions. So, anyways, this is all O levels. We started talking about catalyst. What does a catalyst do? Catalyst reduces activation energy and speeds up the reaction and remains unchanged during the reaction. So, what a catalyst does is it does not affect the frequency. Like the particle is still bumping around at the same rate. But the collisions are now more effective. Like out of the 10 collisions you had previously, only 2 collisions resulted in a reaction. But now out of the 10 collisions, 8 of them are successful. So that means the collisions are becoming more effective. And we started talking about catalysts. We started talking about heterogeneous catalysts. I told you that reactants and catalysts have different states. That's a heterogeneous catalyst. Like N2 and H2 are gases. Fe is a solid. So Fe being a solid is a heterogeneous catalyst. How does that work? The N has a triple bond. It's a very strong triple bond. It's difficult to break. And what the catalyst does is, and what transition metal catalysts usually do is, because they've got more protons, so have this slight tendency to attract electrons. So what this Fe would do is, it would start attracting the electrons from the triple bond. So the electrons in the triple bond are going to get attracted very, very slightly to Fe. That would weaken the triple bond, and the triple bond would eventually break. Same thing happens. The H electrons over here that were being shared between the H atoms, the Fe would slightly pull on those electrons, and the electrons are going to get attracted to the Fe. That was known as adsorption. And the second step was deadsorption, that the weak bonds would eventually break because Fe doesn't attract those electrons very strongly. And if it's not attracting those electrons very strongly, the bonds would eventually break. And in that case, but Fe has done its job. Breaking the triple bond was really difficult, and Fe has successfully been able to break those triple bonds by pulling on those electrons very, very slightly. So the next thing that I wanted to do was a homogeneous catalyst, which which we have already covered previously, but since we are studying catalysts, we'll just go over them. So the reactant and catalyst have the same state. This is one example that you have to remember. And this one example is like you've got I minus 1 reacting with S2O8 and they react to form I2N, 2SO4, 2 minus. Uh, Now this reaction is extremely feasible uh, according to electrochemistry. Like you have I2 plus 2 electrons and they're in equilibrium with 2I minus 1. The E naught for this one is I think 0.54 volts. And you have another reaction where you have S2O8 2 minus, and that is gaining 2 electrons and it's in equilibrium with 2SO4 2 minus, and the E naught for this reaction is 2.01 volts. So both these reactions, there's a higher potential higher potential, remember, likes to gain electrons. So you've got this higher potential which would gain electrons, and you've got this lower potential which is going to lose electrons. So that is exactly what's happening. There's 2I minus 1 that's turning into I2, and there's S2O8 2 minus which is turning into SO4 2 minus. So there's a gain on loss of electrons. You have higher E naught and you have a lower E naught. But the thing is, the reaction is not going to happen. It's got a good E naught cell. The E naught cell is going to be, if you take out the difference, it's going to be 2.01 volts minus 0.54 volts, which is a really high E naught cell, and that's equal to 1.47 volts. So it's a pretty good E naught value. That means the reaction should happen, but it doesn't happen. And I told you that both ions are negatively charged. So the negative ions repel each other, so the activation energy is really high. That it would be very hard for the negative ions to meet. They would be constantly repelling. So you would have to make them very energetic so that they can overcome the force of repulsion that's keeping them away. So they would have to bump into each other with a lot more force. Otherwise, they're going to repel each other. So the reaction has pretty high activation energy and it doesn't happen. TK, is this point clear? Minhail, is this clear? Zoha, is this clear? Ethan, is this clear?
Yes, sir. Yes.
So now the thing that happens is, because both ions are negatively charged, they're not meeting each other. So this electrode is not going to react with this electrode because both of them are negatively charged. So we're going to assume that the two electrodes are not going to react. But when we add an Fe catalyst, we add Fe3 plus or Fe2 plus. So if we add an Fe catalyst in the form of Fe3 plus or Fe2 plus ions, what now happens is that the two electrodes were not reacting with each other, but they would go and react with Fe3 plus. If I make this equation, this is the higher potential and this is your lower potential. So, and I'm going to multiply Fe by 2 so that the number of electrons gained and lost are equal. So anyways, you have a lower potential and you have a higher potential. This electrode would go and react with the Fe electrode. When it does, the reactants are S2O8 2 minus. The other reactant in the first one is Fe2 plus. And the products are 2 Fe3 plus. And the product in this one is 2SO4. It's 2SO4 2 minus. So you have this reaction happening. Let's call that reaction number 1. Similarly, this Fe is also going to react with the iodine equation that's over here. So these two are also going to react. So iodine is going to come along and would also react with the Fe. In that case, the Fe is the higher potential, so Fe is the one that's going to gain electrons, and the iodine one is the lower potential, so that's the one that's going to lose electrons. So you have another reaction that's going on. Iodine reacting with the Fe. In that case, Fe3 plus is the reactant. And in the first reaction, it's 2I minus 1, that's the reactant. And the product are, in the first one, it's I2 that's getting formed. In the second one, it's 2Fe. 2 plus getting formed. So this is what is happening, that iodine goes and reacts with Fe. And at the same time, you have S2O8 also going along, trying to react with. So S2O8 is also going along, trying to react with Fe. Both of them, they try to react with Fe. And that results in this reaction. Remember, S2O8 reacting with Fe, S2O8 is the higher potential, so it gains electrons, while Fe is the lower potential, it loses electrons. When iodine tries to react with Fe, iodine is the lower potential, so it loses electrons, and Fe is the higher potential, it gains electrons. And at the end of the day, you get this reaction. Is this clear, everyone?
Yes, sir.
Yes, sir.
So now, the reaction is the same. The Fe isn't really doing much. If you look at Fe2 plus changes into Fe3 plus, and Fe3 plus changes back into Fe2 plus. So that means you started off with Fe2 plus, and you ended up with Fe2 plus. So the catalyst kind of remains unchanged. It did take part of the reaction, but it kind of remained unchanged at the end of the reaction. So the catalyst kind of remains unchanged at the end of the reaction. So what else? So nothing much is happening to the catalyst. Apart from that, what you'd also notice is that you're getting the same things. The reactants are S2A 2 minus, and there's a reactant which is 2I minus 1. So these are the same reactants. The products are the same. The products were, you were getting 2SO4 2 minus, which you're getting over here. And you had Fe2 plus, not Fe2 plus, I2 getting formed. So that is also getting formed. So if you add up the reaction, both these reactions together, like if you add up this reaction, it is exactly the same reaction. The Fe is only playing a part as a catalyst. Nothing happens to it overall. It remains unchanged. The reaction got divided into two steps. S2O8 first turned into SO4 2 minus, and then I minus 1 turned into I2. But the reaction is a lot faster. Can anyone tell me why the reaction is faster? Anyone, any idea why the reaction is faster now? Like previously you had two negative ions and they were not reacting with each other. So why all of a sudden has the reaction speed increased?
Catalyst positive charge.
Okay, now the reason the speed has increased is that by introducing Fe into the whole reaction and dividing the reaction into two steps, what has happened is that the ions are now oppositely charged. That means they're going to attract each other. So there's no element of repulsion. They would attract each other, and they would attract each other very strongly. I minus 1 would get attracted to Fe3 plus. Fe2 plus is going to get attracted to S2O8 2 minus. So the chances of collisions are going to be really, really high, and the reaction would speed up. So now you've got oppositely charged ions. or oppositely charged reactants which are going to attract each other. TK, is this clear?
Yes, sir.
So this reduces the activation energy of the reaction. So you have to remember this specific example for homogeneous catalyst, TK. Is this clear to everyone?
Yes, sir.
TK.
Yes.
So now, so remember about iron, TK. You have to remember how iron is behaving as a catalyst, as a heterogeneous catalyst in the Haber process, and how ions are behaving as a homogeneous catalyst in this particular specific reaction that you see over here. The third thing that we're going to revise is about it's again from AS. That's your Bronsted-Lowry acid base. Not Bronsted-Lowry, it's the Boltzmann distribution. So we're going to talk about the Boltzmann distribution. Once more. So I'll just give you a quick brief overview of what the Boltzmann distribution is. For example, one second. I said, remember there's going to be a test on Friday on equilibria, TK. So let me copy one image. I think this is fine. Maybe this one. So here's a typical Boltzmann distribution, which is kind of skewed to the right. I mean, it kind of gets dragged along to the right. So what are the two axes? You've got an axis where you have the percentage of particles or the number of molecules. And on this side, on this axis, you've got your energies of those molecules. So imagine you've got a container, and the container has all sorts of molecules. Some would be very energetic, some would have lesser energy. They're all traveling around and bumping with the walls of the container, they're exerting pressure, etc. So imagine a gas or a liquid or even a solid. Now, all the particles don't have identical energy. Some would have low energy. So let's say that's a low energy axis, a point on the axis. Some particles would have high energy. And then what you'll have is some particles having average energy. So most of the particles are going to be having average energies. The height of this graph is the number of molecules. So if you have a container, you've got billions of molecules. The greatest number of molecules are going to have average energy. Very few molecules would have extremely high energy, and very few molecules would have extremely low energy. So the height of the graph at very high energy and at very low energy, that's going to be, I mean, it's not going to have a very big height because in the container, molecules having extremely low energy or extremely high energy, that would be very few. Most of, like if this container is at room temperature, 25 degrees centigrade, then most molecules will have kinetic energy. Remember, temperature is a representation of the average Ke of the molecules. The molecules, not every molecule is going to have 25 degrees centigrade. It's not going to have the same temperature. Some would have energies that would be higher than 25 degrees centigrade. Some would have energies that would be lower than 25. But most would be around 25. In a container that's at 25 degrees centigrade, there would be very few molecules that would have energies that correspond to temperatures greater than, let's say, 100 or 1000, because Extremely high energies, the energies would kind of be uniformly distributed. Now, what happens if temperature increases? When temperature increases, if I increase temperature, if I start heating this up, the number of particles at high energies would increase. So the graph is going to start rising up because now the container is getting heated up. So the number of molecules that had high energies, that's going to be more now because the temperature is higher. The average energy would shift to the right because the average energy would also increase. If you start heating it up, previously the container was at 25, now it's probably going to be at 35 or 45 or 55 at a much higher temperature. So the average energy of the particles would also increase. And the number of particles having low energy, that's going to go down. There would be a lot less particles having low energy now. Is this point clear?
Yes, sir.
ठीक है, Lubena, is this clear? Adam, is this clear?
Yes, sir.
So three things would happen. The graph would start
Yes,
rising.
sir.
So the graph would start rising up over here because you have more particles having high energy. ठीक है? Remember, the height of the graph is the number of molecules. So more particles having high energy, fewer particles having low energy, and the average energy would also shift to the right. So the graph is going to get skewed in this direction. The height would increase on the right side, it's going to drop on the left side, and the peak, which represents the average energy, that would kind of shift to the right. So that is what is going on at higher temperatures. This is the curve at, this is the same curve at higher temperature. And similarly, what happens if you decrease temperature? If I start cooling this, now you'll have more particles having low energy. So the curve would start to rise sharply. One second. I can't really, maybe I should copy one diagram, just a second. This one kind of sums it up. So this one kind of sums it up. The curve would start shifting. It would start rising from this side, dropping from this side. Instead of velocity, I think we should write the energy or the kinetic energy of the molecules. Instead of probability, we should write the number of particles, the number of molecules. Having a particular energy. So this is what's going on. And you'll be asked a few questions about catalysts. What do catalysts do? Remember, catalyst is the only thing that you could actually show on this graph. I just hold on, wait 1 minute for the azan. ठीक है साकिब, इस क्लास के बाद. So let's start. Um, I said you'll be asked two things. The only thing you could actually show on this, one second, is this mute or TK? As the only thing you can actually show on a Boltzmann distribution is it's the distribution of molecular energies. But you can show the effect of a catalyst. That's the only thing that you could actually show. Or you can, I mean, you can show a couple of things. You can show the effect of increasing temperature, decreasing temperature, and you can show the effect of catalyst. What you can't show is the effect of surface area or the effect of adding increasing pressure or changing concentration. Those effects cannot be shown over here. In a Boltzmann distribution, the only thing that uh, uh, can be shown is temperature and the effect of a catalyst. So catalyst is you've got particles, energetic particles. Remember on the right side, these are the molecules that are energetic. You've got very few of them. Okay, the height is the number of molecules. So you've got very few energetic molecules. Most of the molecules have energies that are really low. Okay, so you've got more molecules over here. Very few molecules having high energy that is greater than activation energy. So the reaction is slow. What happens when you increase temperature? When you increase temperature, the curve shifts to the right. The number of molecules having energy greater than activation energy, that increases. So this is one thing that you can show. So at higher temperatures, more molecules are going to have energies that are greater than the activation energy, which is EA. Another thing that you can show is the effect of catalyst. So what does a catalyst do? Let's focus on the red line. Now, when a catalyst is added, the activation energy decreases. It shifts to the left. So that's your EA with a catalyst. Now you don't need that much energy. So when a catalyst is added, more particles can take part in the reaction. Even these particles can now take part in the reaction. So catalyst decreases activation energy. So all of a sudden, these molecules were initially these red ones were able to take part in the reaction because they were energetic enough. But now the energy that is required has now decreased. So even these particles that are slightly less energetic, they can even take part in the reaction because they've got energy that is greater than the activation energy. So catalyst decreases EA. So more particles now automatically have energy that is greater than EA. So is this clear to everyone?
Yes, sir.
Yes, sir.
So all of this was old AS stuff, TK. So most of it was O-levels AS that you've already covered. The catalyst part was probably done in the electrochemistry part was actually done in when we were studying electrochemistry. Now what we're going to do is okay, just hold on one second. Just a second. Today. Now what we're going to do is we're going to start with A2, rate of reaction. Now in A2 there's a thing called an order of reaction. So we've learned that everything depends on collisions. That when two things react, So for example, you've got X reacting with Y and they're producing Z. So it all depends on the collisions between X and Y. So you've got X and you've got particles of Y, and they're going to bump into each other and they're going to collide with each other, and that would result in a reaction. So these particles would react with these particles. Now the thing is that the rate of the reaction depends on the concentration of these particles. It depends on the concentration of the particles of X. Remember, square brackets is concentration, and it depends on the concentration of the particles of Y. If the concentration is larger, greater, then obviously the number of collisions would increase. Here we already studied more concentration. That would obviously result in more frequent collisions. And if there are fewer particles, if the concentration is lesser, then obviously the number of collisions is also going to be a lot lesser. So the speed with which the reaction happens depends on the concentration of X and the concentration of Y and how much are they bumping into each other. So that is one thing that they depend on. But how will that affect the rate? The relationship is not a linear relationship. It varies a lot. So there's power A and there's power B. That's known as the order of the reaction. That basically determines, like if I independently assess that rate depends on the concentration of X and the power is A. A determines how is that depending on it. Like if you increase concentration of X, how would the rate increase? A is known as the order, and A is going to have, we're going to study three values. A can have a value of 0, that is 0 order. A can have a value of 1, that is first order, and A can have a value of 2. So A determines how the concentration, like you're changing the concentration of X, how would the speed of the reaction be affected by changing the concentration of X? We know that if you decrease the concentration of X, the rate of reaction should decrease. I mean, that makes sense. Like if you decrease concentration, if you increase concentration, the rate of reaction should increase or decrease proportionally. So if A is 1, that's known as first order. And if A is 2, that's known as a second order relationship. So every reactant is going to have an order. Let's talk about 0 order first. Like if you have rate dependent on the concentration of X and the power is 0. What a 0 order reaction means that no matter what you do to the concentration of X, you increase it, you decrease it, anything to the power 0 is 1. So that means the rate is going to remain unaffected. What that power 0 means is you put in any value of X. I mean, you increase concentration of X or you decrease concentration of X. The rate of the reaction, nothing would happen to the rate of the reaction. The reaction would happen at the same speed. So 0 order means that rate is simply not dependent on the concentration of X. Like it has nothing to do with the concentration of X. So if you continue to change the concentration of X, the speed of the reaction, nothing would happen to it. So is this clear what 0 order means? Is this clear to everyone?
Yes, sir.
Yes, sir.
Now similarly, you've got rate is first order, power 1. Now that's a linear relationship. That means you double the concentration of X, the rate would also double. I mean, that makes sense. Like if you increase the number of particles of X, you'll have more collisions and the reaction is going to be a lot faster. So that's a linear relationship. So that's order one. It's a linear relationship. So whatever happens to X, the same thing happens to the rate. You decrease concentration, the rate also decreases. You increase concentration, the rate also increases. So it's a linear relationship. Uh, X concentration doubles, then the rate also doubles. Or vice versa, if you decrease the concentration, then the rate would also decrease. And then there's order 2. An order 2 relationship is that the rate is very sensitive to the concentration of X. It's squared. So that means that's a quadratic relationship. So what that means is you double the concentration of X. Like if you, instead of having X, you make it 2X, remember it's being squared. So the rate is going to be 4 times now. So rate doesn't just double, it rate becomes 4 times, or what you can say is rate quadruples. So it's a square relationship. I mean, whatever happens to rate, that's going to be a lot more than what's happening to the concentration of X. You double it, rate becomes 4 times. Similarly, if you triple the concentration of X, what is C square? Rate becomes 9 times. So rate becomes 9 times. If you triple the concentration of X, a rate would become, so it's a square relationship. Similarly, if you decrease the concentration, like you decrease the concentration by half, then rate decreases by 1/4. So that means rate is a lot more sensitive to the concentration of X. Whatever you alter the concentration of X, rate changes accordingly, but twice as much, or in terms of square. You double it, it becomes quadruple. You triple it, becomes 9 times. You half it, if you halve it, the rate decreases by 1/4. So it's not a really linear relationship; it's a quadratic relationship. So you've got zero order, where rate is not affected by anything that you do to the concentration of X. Whatever you do, the rate remains completely unaffected. You've got a linear relationship where power is 1, that's order 1. Whatever you do to X, the same thing happens to rate. You double it, the rate increases by 2 times. You triple the concentration of X, rate also triples. And then there's a square relationship. That is, so every time all these reactants, they've got these 3 orders. It's either 0, 1, or 2. These are the ones that we are going to study. So whenever you see a reaction, remember the rate is not dependent in a simple way on the concentration of X or Y. It has a power, it has an order, and that determines what's the relationship between the reactant concentration and the rate. Is this clear? ठीक है, Minail, is this clear? Zoya, is this clear? Adam, is this clear?
Yes, sir.
ठीक है, we'll talk about
Yes.
चलो ठीक है, we'll talk about orders now in the next class, ठीक है? ठीक है, okay, Allah Hafiz. Adam, yes, I will recommend that because if it doesn't really matter, like P5, it's just a 9.5%, and it doesn't carry a lot of weightage. So I would recommend it because I mean, going for P5 is not really going to matter anyway. ठीक है, it's not going to be a plus point because if they're allowing exemption, so then it's I think you should take it. I mean, this is going to be less of a burden, ठीक है? Clear है? चलिए ठीक है, okay, take care everyone.
Thank you, sir.
Allah Hafiz.
Thank you.